what's going on here? Simulating random processes up the top here. Gee, that's a mouthful. Wonder what that means. Let's look around the screen for a bit here and lock into the word simulating. Simulating means mimicking. Well, not doing the real thing, but doing something similar. Simulating. All right, well, I'm interested over here in flying one of those. I don't think I have much of a chance. Maybe they will put me in front of a flight simulator. It looks like the cockpit of a plane, but it isn't. We could pretend we're flying, pretending or simulating. And over here, we could use a coin maybe or a die to actually simulate some processes that might be going on. And what about here? Well, there's the process that we could be doing. We could use a die to actually mimic a game of cricket, or to simulate a game of cricket. We're going to do that later on. Dice cricket, you might have actually done that. So there's the question, why do the real thing? Okay, why would you do it? Or perhaps why wouldn't you do it? Why would you want to simulate it? Well, here's the answer to that. To do the real thing might take too long. Okay, to do 50 tosses of a coin, could we do that electronically more quickly? Or too expensive to go and fly that plane to practice? We could use a simulator, won't be actually using any fuel or stuff like that. Or it could just be too hard to do the process and see how it all turns out, if you like. So what we're going to be doing here is simulating, mimicking, if you like, the situation to see in the long run what would happen maybe, and without actually doing the empirical measurement that we did in the previous videos there on probability. So we're really talking about working out experimental probabilities without doing the experiment. Okay, experimental probabilities without doing the experiment. And what we're going to be doing is looking at random processes only, simulating those things that seem to have a randomness in them. And like, what would you expect with the toss of a coin? Are you going to do it 100 times, or can we simulate that and check out the idea that half should be heads and a half tails? But that's what we're doing. Too long, too expensive and too hard to do the real thing. Why do it? Let's see if we can simulate it. Okay, come down here a bit and let's have a look. There's basically two types of simulation we're going to be talking about in this presentation. The first one is a mechanical one, where you maybe simulate the game of cricket with two dice, and we're going to do that later. Or an electronic one, where you use a calculator or a spreadsheet to actually do many trials of the experiment in a simulated form. Okay, again, you could be checking out the probability of getting a 6 on the roll of a die or something like that, and rather than do it 100 times and see how it all works out, we could do it electronically. All right, so let's go down now and have a look at some of these. All right, here's the one I've been raving on a bit about, and you might have seen this before in junior maths. Mechanical simulations here. So here we are, dice cricket simulated with a die. The original game is played between two people. The success or failure of a team depends on the outcome of rolling a single die. Okay, there are 10 partnerships per innings, and the players in a partnership score according to this system here. Now, while I'm raving on about this, I want you to think about the appropriateness of simulating a cricket game with the roll of a die. Okay, think about that. Okay, it's got something to do with the title of this presentation, which is Simulating Random in Processes. All right, here we go. 1 on the die scores 1 run. Guess what? 2 on the die scores 2 runs. 3 on the die scores 3 runs. 4 on the die scores 4 runs. Getting bored. 5, however, oh, here's something interesting. It terminates a partnership, and if you get 6, it scores 6 runs. So those are the rules. Hopefully you might have seen something like this in junior maths. So what we're doing is doing a mechanical simulation of a real life situation there, playing cricket. And there's something fundamentally, mathematically very wrong with it. I wonder if you've spotted it yet. Anyway, here are your questions. I want you to play it with a partner, and there are the instructions. You're going to play one full game, so that's 10 partnerships. Keeping scores, each player should take a turn at batting. You can click on the icon in your book if you want to play games more quickly. So that's going to be an electronic simulation, isn't it? Does it also suffer from the problem that this one does? Think about that. Record any observations which result from playing of the game many times. So you want to talk to your teacher about that with other classmates and see what you think. Now, but I want you to tell me right now what is fundamentally wrong with this simulation. Okay. Pause it, think about it, have a chat, and now I'm going to tell you. We are, if you like, simulating a game with a random process, a mechanical process which gives a random set of answers. Okay, is cricket played that way? No. You adjust your playing style according to the bowler, according to the wicket, etc., etc. There isn't too much randomness in the way you play cricket. Maybe the way I play cricket there is, but don't want to go there, mate. All right, let's keep going and have a look at the electronic simulation of stuff. Okay, now, this has raised an interesting question, because you want to simulate random processes. So every number or every situation has an equal opportunity of coming up. That's what random means. Equal chance of the set of outcomes coming up. Random. Okay. So how do you get a calculator or a spreadsheet to generate numbers or random values that can represent numbers or situations in your simulation, in your real life thing? Well, it's only pseudo. A lot of words here, mate. It's only a pseudo random process. So pseudo means not real. Okay? It's an imitation. It's not the real thing. And why isn't it? Well, in your calculator, which we're going to use in a minute, there's been a software package or a program put in which imitates randomness. It's actually very predictable. If you looked at the program, you could work out what numbers were going to come up. So it's only a pseudo random number generator. So we are going to do this electronically. Okay, so let's have a look at using this electronic approach to simulation. So here's a Casio 9860 Plus calculator, and I want to take you through the steps to generate random numbers. And then we're going to say, well, if we can generate random numbers, they could represent random outcomes in some situation. So here we are, up here now, we've got the run mode. Okay, so what I'd like you to do then is to get that up on your calculator, and then what I want you to do is to hit the option key in there. And if you hit the option key, you get this window here, and we've got to go to the next window there, and this is what we get, and we're going to try to find a random number generator. Now this is all to do with statistics and probability, so guess what? We're going to choose probability, which is F3 there, and we get this window, and there it is, sitting there, rand. So if we hit F4, we come to this window down the bottom here. Let's have a look, and there it is, random with those crosses means that's often used to stand for number. So it's a random number represented by that key. So we're going to hit F1, and up comes that command accessing that program which is going to generate random numbers. Sort of, it's a pseudo generator, isn't it? Because we could predict, looking at the program, what number would come up next. That's the best we can do in mimicking or simulating randomness. All right, so there we are, random number. And if you then hit execute, then that program will pluck out a random number, and we've got one there for 10 places, or 10 decimal places there, which is the maximum display on this particular calculator. And if we keep hitting execute, down they come, one after the other, and what do you notice about them? Well, they're all decimals, mate. No whole numbers there, so that's pretty inconvenient to work with. So at least we've got some randomness coming up there, even if it's pseudo, but let's tidy the numbers up a bit perhaps. Okay, so what I want you to play with now are some other possible commands to put with random number. So accessing another program in the calculator or a couple, and see if we can tidy up the sorts of numbers we want. Because guess what? If you're rolling a die and you want to simulate that electronically, what will you do? Well, you want numbers 1 to 6, mate. You don't want these decimals. How can they represent the sides of a die? So we've got to tidy up a bit. All right, so I want you to play with these commands. So 6 random number, the first one is that one. I want you to put down what sort of numbers you think that is generating by hitting execute maybe 10, 15 times. It's easy enough done, nice and quick, and have a look at the numbers that you're getting, and then see if you can understand why this command would generate those numbers. Then I want you to try this one, 6 random number plus 1. Okay, so you need to go through the steps as I did there and just add these little pieces. All right, so let's have a look. And we'll pause it for a minute now because I want you to do those, and I want you to do it about at least 20 times each. And you to study what this electronic pseudo-random number generator is producing. And then we might be able to use it to simulate some real-life situation. All right, come down here now and see what I got. Okay, here's the first one. Did you get this? 6 random number. Numbers generated are between 0 and 6. Now, does that make sense? Let's have a look at the command. You might have realised random number generated numbers, not 0, but between 0 and 1. Not including 0 and not including 1. So if you put a 6 in front over here on this window, if you put a 6 in front, guess what? I think you're multiplying, eh? So it's going to be 6 times 0. It's starting somewhere a little bit above 0 and going through to 6, but not reaching 6, because it's 6 times the set of numbers which will be produced by random number, and random number goes from 0 to 1 but doesn't reach 1. So this is going to go from 0 to 6 but not reach 6. Did you get that? Okay. I want you to use this approach to understand what the programs are doing. Okay, so let's look at the next one now. 6 random number plus 1. Okay, did you get this? I reckon the numbers generated are between 1 and 7. I've only got a lot of bundles of 3 here now. All got 3 points in them. But anyway, not to worry. No doubt it comes good later. Why would we say generated between 1 and 7? Let's study the command. We're building up a little bit of knowledge here. 6 random number generates numbers from 0 to 6, not including the ends. Now we're going to add 1, so it's going to be, if we add 1, it's going to be numbers between 1 and 7. Okay, and not including 7. Okay, right, so did you get that? Let's go and look at a couple of other commands now. Okay, well here's one. Oh, look at this. Number 3 here is int 6 random number plus 1 in brackets. Where did this thing come from? Well, that's another program which makes integers out of the numbers generated by 6 random number plus 1. This is powerful, isn't it? Because those decimals hanging off all those random numbers are inconvenient to work with. If we can generate integers, we could simulate nicely rolls of a die. That'd be good. So here we go. We go back to run mode in there, and we're searching for this command, int. Okay, so this time, again, we hit options. We get this window in here, and we've got to go to the next page there, the next window, which is this. And this time, I've left out a window there. This time, you've got to go to number. I've left that out there. So here, when you go to the next window, there will be an option. If you hit number, you get these set of options in this window. So left that step out. Sorry about that. All right, so if you go there, you want to choose int, that one there. Not integer, not int. Okay, you want int. Okay, so if you hit F2, you get the command sitting up there. Right, so now we want to add some stuff to it. So if we execute that, we come down to here, and we can then put in brackets after it in the same way as I did before, bracket 6 random number plus 1. Okay, we need the bracket because we want the calculator to generate all these numbers, and we want to then feed it into this other program so that we just produce integers. So I want you to investigate this now and see what sort of things come up, and you might make your own conclusion there as to what the program int actually does. Okay, so let's come down and have a look. Did you get this? The numbers generated are integers between 1 and 6. Now, how do you think int is working then? Let's have a look. We said 6 random number plus 1 produce numbers between 1 and 6, all decimals. Okay, oops, 1 and 7, isn't it? Naughty, naughty. Between 1 and 7. So what's random number doing, what's int doing if it's producing integers only between 1 and 6? I hope you did about 20, numbers 2, 5 and 3 here, but you'll never get a 7. How is that so? Well, let's have a look. We said right up to 7, but not including it. So that'd be 6.9987, whatever. And so what int must be doing is if it doesn't make an integer, doesn't get high enough to the next integer, it rounds it back down to the preceding one. Okay, so 1.99 would become the integer 1. 2.01 goes back to 2. Hey, that's not bad because guess what? 1 to 6 are the numbers you get from a die. So here's a nice simulation, electronic simulation, of rolling a die if you kept doing this. You might like to do it and see how many rolls it takes to get close to the a priori theoretical probability of 1 in 6. Okay. Okay, did you see that? Well, that's a powerful one. Let's go down and have a look at some more commands. Okay, here's another dude here, and I want you to put this on your calculator in the same way, and maybe before you do that, you might have a look at what your expectation is of this set of commands. What do you actually expect? Okay, so we've put the 1 outside now, mate. What's going on there? Will that give the same sort of result? So we're going to make integers out of 6 random number, and then we're going to add 1. Okay, make up your little hypothesis now, and we'll check it. Okay, so come down here. I've got some here. All right, so it looks pretty much the same on this screen, but you did 20, so you might see a better pattern, get a better look at the pattern. So the numbers generated here are integers also between 1 and 6, done differently. Can you understand that command? So 6 random number gives you numbers between 0 and 6. Now, if we make integers out of them, then you're going to go from 0 to, remember we don't get quite up to 6, do we? 5.99. So if we make an integer with int command, that brings it back to the next integer underneath. So that would generate 0 to 5, and then if we add 1, oh yeah, that's how we get it. It's 1 to 6. Get that? Because I don't want you just to learn off in monkey fashion the commands. I'd like you to think at least about what they're doing. Okay, it's beyond the scope of this course to look at the program that's running there. Okay, we don't do programming here. All right, so let's go down and have a look at another one. So there's another possible command to simulate a die, the results of the throw of a die. Okay, so here's another one. Now this is getting interesting. You're going to have to watch this. This is going to be a bit of a tricky do here, mate. Okay, so your command is that this time. So there it is, entered in, same process. If you're getting lost, you might go back and look at the earlier part where I showed you how to find int and ran. But I want you to do this one 20 times as well. And be careful, this is going to get tricky in a minute. Here we are, the numbers generated are between 0 and 1. let's unpack that. Okay, so let's do here random number gives you 0 to 1 but less than 1. Then we're going to add 0.5, so it's going to be 0.5 to 1.5. All right, and then we're going to int it. Now what would 0.5 be? It's not big enough to be 1, so it's got to be taken down to 0. And 1.5 is the max, so that has to go down to 1. And everything in between will go down to 0. Ooh, so this is an interesting way of generating 0 and 1. Now, do you think you're equally likely to get zeros and ones out of this command? That's the question. Okay, I want you to take a little guess at that, because here's a challenge for you coming up. And pay attention here now. We've got this one. I'm going to stick 0.9 in the hole there instead of 0.5. What would you expect to generate here? And would you expect to have them generated with equal frequency? Okay, make up your hypothesis. You reckon rounding, etc., etc. Okay, let's have a look at what happens now. Or have a go. Let's have a look at what happens now. Okay, there's the command, and I'm getting 110. I only did it a few times. You did it 20, and was it true that they both came up with equal occurrence, with equal frequency? Numbers generated are all noughts or ones. Let's work it out. Okay, watch this now. The random number generates numbers between 0 and 1, but not including 1. Now we're going to add 0.9, so we're going to generate numbers between 0.9 and not including 0.9, and 1.9 and not including 1.9, in between, strictly between. Okay, and then we're going to do int on that. So what would 0.9 go to? That would go to 0, and 1.9 would go to 1. You say, Huddy, this is getting boring, the same as last one, mate. But here's the tricky do. Is it going to generate the same number of ones as zeros as, I'll tell you the answer to the previous one, 0.5 does, because it's right in the middle. Let's see if we can understand it. Okay, let's draw a little diagram here. Random number generates in this gap here. All right, a little diagram on number line. I just wrote that out. Okay, so 0 to 1. Okay, and then when we add 0.9 to it, we need a little bit bigger space down here now. 0, 1, and 2. So I'm going to block in now. It goes from 0.9, which is in here, like 0.1 back from 1, 0.9 up to 1.9. That's our region where we're generating. But look out, it isn't evenly distributed about 1, is it? Okay, so what's going to happen to this batch in here? Between 0.9 and 1 are going to be called zeros. Remember, int gives you an integer under the value. Okay, the next integer below the value. And this up here is going to give us ones. Hey, look at this. There's going to be more ones than what there are zeros because of the difference in the gap. So zeros are going to come up 0.1 of the time, and ones are going to come up 0.9 of the time. Hey, now this is powerful, where you don't have equal probability of the particular outcomes in an experiment. You can, if you like, weight it one way or the other. Okay, let's have a look now at doing an actual example with that. Here we are. If each day of the week is chosen in a random manner, what's the chance it is a weekday? Well, you can do that with theoretical probability, can't you? Okay, there's 5 out of 7, isn't it? Okay. But if you were trying to simulate that and do an experimental probability calculation on it, you want to do it many times. So how would you do it? Well, let's try to simulate that. Simulate many choosings and see how long it takes for it to come to 5/7 and 2/7, which is our expected probability. Well, I'm going to do it mechanically over here. Okay, mechanically we want randomness here. Construct a pack of 7 cards. Here, I'm going to have a pack of 7 cards where 5 are marked weekday and 2 are marked weekend. And if you keep shuffling it, so we're not stacking them up in any particular order, so it's not biased. We want, I want to put that word down. That's something you learned in the first presentation, isn't it? We want unbiased results here. Okay, so you will pick a card, record it, return it to the pack, shuffle it, and so on. Okay. What about electronically? Well, I guess you can see that we are able now to simulate a situation where one outcome has a probability of 5/7 and the other outcome has a probability of 2/7. Let's have a look at it. We're going to go random number for a start. Then if we add 2/7, have a look at the diagram. It all moves up here, up that way. And then if we find if we int it, then these below 1, from 2/7 up to 1, will become zeros. And from 1 to 9/7, right, because adding 2/7 to 1 is 7/7, plus 2/7 is 9/7. So they will be rounded back to the next integer, and they will be 1s there. And will they come up with equal likelihood? No. This bunch here is only 2/7 of the line, and this bunch is 5/7. So what does that mean? A 0 will represent the 5 out of 7 weekdays, and a 1 will represent the 2 out of 7 weekends. So we can we can do this simulation many, many times and see if our theoretical probability of 5/7 and 2/7 does come up and how long it takes to come up. Okay. Would you expect, this goes back to the first presentation, would you expect in 7 choosings, either done mechanically or electronically, would you expect exactly 5 weekdays and 2 weekends? Would you expect that in exactly 7 choosings? So you might talk to your teacher about that, talk to other students about that. Just remember, this is a random process, and that might affect how you think about that. Okay, so come on down now, and we've got the last little thing for you. Okay, this is that simulation on the calculator, where we've got that. And what I'd like you to do is to do many choosings and have a look at the pattern. And let's look at the first 7. Did you get 5 and 2? In 14, did you get 10 and 4? What's going on there, mate? Okay, how many do you have to do before you get to that 5/7 and 2/7 proportion? Okay, I hope you have fun with that. It's an interesting little aside, and simulations can be very powerful in real life, where answers to complex situations want to be found, and you haven't got the time to do the experiments to see how it's all going to turn out. So hope you've enjoyed that. Cheers for now.